Okay, and next we have group 4, who's going to tell us about asymptotic invariants of symbolic powers.
Well, hey everyone, I'm Mariana, this is Lizzy, and Charlie, and we are pleased to present you our work on asymptotic invariants of symbolic powers. This work has been developed in the reunion that we are hearing now, the REU, in commutative algebra, and I first wanted to thank all the organizers and all the people that make this possible, all the mentors that give us the opportunity to do math, to learn how to do research, to make this wonderful community, and to give us the opportunity to do it here in this rich environment at beautiful Guanajuato. So let's go through the math. First of all, I wanted to tell you about our project goal. First, we need to take care about some kind of a specific family of ideals and a Grant function. So our goal here is to compute its asymptotic behavior through this limit. So the families that we care about is binomial H ideals, initial ideals related to the binomial H ideal, and its symbolic powers, something that I'm going to define a bit later. Now, first of all, fix an order, a term order, to be able to compute the leading monomial of certain polynomial that is not 0. And then with respect to this term order, we can generate an initial ideal by all the leading monomials from the binomial H ideal through this term order. So in this particular talk, we are going to take the lexicographic order. Is that okay? Now, let's go to the second family. The multigradient in the ring is defined as fixing the degree of all the variables equals to this, I'm going to call it a basis of the vector space, in this case, the n to the n, the natural numbers to the n. So what does the degree actually work? If you're thinking about the degree as a function, this function is going to recall how many factors of the variables are in each of the components. For example, we know how this looks like, right? So we have a 1 in certainly component and zeros everywhere else, right? Now, how we define the generic initial ideal is putting all these variables and we generate it when this is a path in the graph. Now, for the last one, we care about the symbolic powers, and it's in the title, so this is important, right? We take an ideal that is a radical one. We have its decomposition, and we define its symbolic power as the intersection of all the minimal primes to the m symbolic power. But these guys are defined as all the elements, but on their product, they're still in this ordinary power, but for some q that it's not in a one ordinary power. So that's the way we define it here.
So now to define some of the asymptotic invariants that we were interested in looking at. The first one was called the Waldschmidt constant, which is defined in terms of the initial degree of some homogeneous ideal. What this is it's just the smallest degree of any element that is in your ideal. And the Waldschmidt constant quantifies how fast the initial degree of some ideal grows as you take larger and larger symbolic powers. And it can be shown that it exists for any ideal. The next thing that we were interested in looking at was the asymptotic regularity. So for the experts in the room, the regularity of an ideal is just the number of rows in its Betty table. But for the ideals that we were interested in looking at, it was, roughly speaking, the maximal degree of a minimal generator of the ideal. So what the asymptotic regularity does is it quantifies how fast the regularity grows as you take larger symbolic powers. And while we don't know if it exists or it doesn't necessarily exists for just your general homogeneous ideal, it does exist for monomial ideals specifically. So our project, we were trying to determine what the Waldschmidt constant and asymptotic regularity was for binomial edge ideals and their associated monomial ideals, like initial ideals and generic initial ideals. Some of the very first results that we were able to get was to show that for all binomial edge ideals and their initial ideals, the Waldschmidt constant is equal to 2. The proof of this is actually quite straightforward. You can show that the mth symbolic power of any binomial edge ideal is contained in the mth symbolic power of the binomial edge ideal associated to some complete graph. And when you have a containment like this, you can say that the Waldschmidt constant of the smaller ideal is at most the Waldschmidt constant of the larger ideal. You can also show that the Waldschmidt constant of the binomial edge ideal for the complete graph is 2, and that for any of the ideals that we are interested in, the Waldschmidt constant for any of the ideals is bounded above by 2 as well. So you end up with this case where the Waldschmidt constant is bounded both above and below by 2, and so it's equal to 2. And the exact same argument works for the initial ideals. We were also able to show that for closed graphs, the asymptotic regularity of the binomial edge ideals and the asymptotic regularity for their initial ideals is equal to 2. And also that if H is an induced subgraph of G, then the regularity of the symbolic powers for the binomial edge ideal for H is less than or equal to the regularity for the symbolic powers of the binomial edge ideal for G. So in particular, the asymptotic regularity of the smaller graph is less than or equal to the asymptotic regularity of the parent graph. So now on to something that we tried very hard to show, but we're unfortunately unable to do so. This right here is a picture of the net graph, and we believe very strongly that the asymptotic regularity of its binomial edge ideal is equal to 3, but that was not something that we were able to show.
Okay, so now you've heard a lot about the asymptotic invariants as they relate to binomial edge ideals themselves, but this object right here will be useful for talking about the asymptotic invariants in relation to monomial ideals that are related to the binomial edge ideal, like the generic initial ideal or the initial ideal. And so specifically for like a radical monomial ideal, right, we have this prime decomposition, and for each one of these primes, we're going to associate to it some inequality. And so specifically, we're looking at the components in n-dimensional real space. So n is the number of variables in our ring that we've adjoined to our ring. And we're saying that all the components have to be greater than or equal to 0. We're also going to sum up all the components corresponding to variables that are in the given prime. And when we sum them up, then we're going to ask that the sum is greater than or equal to 1. And so this gives us a ton of different facets that we're going to, or half spaces that we're going to intersect to get this convex body. So these are examples of the convex bodies in free space for different ideals. And here you can see that they have facets here, which are like n-1 dimensional faces, and vertices here, which are 0-dimensional faces, and then also these edges. Here we're using face to mean something more general than what you might be accustomed with, because for most cases this symbolic polyhedron is in really high dimensions. And so why do we care about this? Well, we're given the facets of the symbolic polyhedron by the primes, and if we look at the vertices, we can compute directly the Waldschmidt constant and the asymptotic regularity by just summing over all the components of the vertex, and then looking at the minimum over all vertices. And by the way, when I'm saying vertices now, and for the rest of the talk, it's going to refer to vertices of the symbolic polyhedron, not vertices of the graph that it's associated to. And we're using this calligraphically to describe that. And so here, if I is a square free monomial ideal of k join x1 through xn, and A is a vertex, then A lies on at least n facets of SP of I. And this is just like some linear algebra here. What I mean by this is if A lies on F, then the defining inequality of facet F, that defining an equality coming from a prime, it attains equality on A. So we prove this one-to-one correspondence between the vertices with only zeros and ones of SP of I and the minimal generators of I. So sometimes the vertices, the components may be looking like 1/2 or 1/3, but when it's only zeros and ones, we know it's going to be a minimal generator and vice versa. So we have this corollary that the regularity of the generic initial ideal of JG is greater than or equal to L, where L is the length of the longest induced path in G. And when I am talking about induced paths, I have to be careful because, okay, for example, the cycle graph on 5 vertices, the longest induced path here is not 5, it's actually 4. And that's because, you can look at like these vertices, and these are 4 vertices, and when you look at the induced graph, it's a path graph. But if I were to include like this 5th vertex, yeah, the induced graph is no longer a path graph, it's a cycle graph. So in general, cycles have a length of the longest induced path is 1 less than the number of vertices. And our conjecture is actually that for all graphs, the regularity of gen of JG is equal to L. And then we have these theorems that we use a lot in our results. The first one is that if we have any induced subgraph of G, and this works for both generic initial ideal and the initial ideal, we have this kind of inclusion between the vertices of the symbolic polyhedron associated to H with the vertices of the symbolic polyhedron associated to G. And I here is a canonical inclusion because technically the symbolic polyhedron here is living in a lower dimensional space. So we kind of send like different dimensions to their corresponding dimensions in G. And then here, this theorem is saying a little bit more. Suppose G has connected components, so it's a disconnected graph. And then again, for both gen and initial, under the canonical inclusion, we have that the vertices of G are just the vertices coming from the connected components of G. So of course, this theorem says one direction of this equality, but this lower theorem is actually saying that all the vertices that you get are going to be coming from the connected components. And we can combine these results into some corollaries.
Okay, so this first corollary talks about what are called full vertices, which I'm going to define in a second. But basically, you look at a vertex and you go through each coordinate and you say, if either one of the x coordinates or the y coordinates is non-zero, then I put it in the set V sub H sub A. And this corollary says that if I take that vertex set and induce by it, I end up with a connected graph. So we call a full vertex specifically the case when VHA is equal to the vertex set of the entire graph. And that gives us a decomposition of the vertices of the symbolic polyhedron as the inclusions of the full vertices of all of its induced connected subgraphs. So I take all H in this fancy H the set of induced connected subgraphs. And now I can calculate the asymptotic regularity and the Boltzmann constant as the max and min respectively of the maximal and minimal sums of the vertices, of the full vertices for the induced connected subgraphs. And here is a really nice reason why we would like to care about full vertices. So if you compute the full vertices of the complete graph, there actually turns out to be only 1. And so an intuition behind this is that remember that in GIN, you have paths being the generators. And in the complete graph, since you have a path that's one edge between any two vertices, none of the y's are going to show up as minimal generators. So that's why all of these are zeros. And then it's not hard to see that you have primes that give you every edge x as being, you take all the x's except for 1. You have now n inequalities where you have sum over all the x's minus 1 of the x's is greater than or equal to 1. And then it's not so surprising that the best you can do to solve that and minimize this sum is set every variable equal to n over n minus 1. So that's how you get the Boltzmann constant and the asymptotic regularity, because now I'm just taking the maximum and minimum of these sets, because every induced connected subgraph of the complete graph is just another complete graph. And so now we have this other proposition, which gives the Boltzmann constant for the gin of a complete k-partite graph, which is k over k minus 1. And the intuition for that is basically there you show an upper bound over k minus 1, and then you invoke one of our theorems, specifically the one about subgraphs, because if you just pick one vertex in each of the k partitions, and then you reduce by it, you just get the complete graph on k vertices, which gives you a vertex with k over k minus 1 as the sum. And then this actually combines into this theorem that extends a result given in this paper with a bunch of people, including one of our lovely organizers, for gin, where they did it for the edge ideal. And remember that since gin contains all the edges, this is a strictly bigger than ideal. So basically what this says is that I have the Boltzmann constant of gin being greater than or equal to the chromatic number over the chromatic number minus 1. And for some intuition on how that works, remember that the chromatic number is basically the smallest number of partitions that you need to get a k-partite graph. And so as an example of how this, the theorem works, you have this Peterson graph, everyone's favorite if they say graph theory, and you have a 3 coloring on it. And basically what you do is you take you try to find independent, irredundant disconnecting sets of this graph that contain the irredundant disconnecting sets. Oh, okay. Is it? Oh boy. Actually, that's fine. It doesn't even matter. Okay. This is a 4 coloring. The optimal one is a 3 coloring, but we don't even need that. Because what we do is then we correspond with the 4-partite graph in this case of 3 partitions. Okay. Sorry. Take your time. Blue. There we go. Okay, now we have 3 partition. So we have 4 blues, 3 oranges, and 3 reds. And then we look at the complete k-partite graph with 4, 3, and 3. And then I remove all of the vertices except for 1 color, because those are the irredundant disconnecting sets of the complete k-partite. And then I just keep adding things back in until I have decreased the number of connected components. So in this case, let's say orange. I go 1, 2, 3. I can add this guy back in. I can add this guy and this guy back in. And then I'm done. And so I have an irredundant disconnecting set now for this graph, which corresponds to a facet where the inequality being satisfied here implies that the inequality of the other one is satisfied, because I can now pick the x coordinates in each connected component that don't correspond to the orange one, because that's how you make facets. You pick in each connected component 1 minus, the number of x's minus 1 in however big the connected component is. And so now that we have this bound, we can actually extend it to more of the results that were in the same theorem, which is that if you have a weakly perfect graph, meaning that the clique number and the chromatic number coincide, then this theorem is going to imply that you have an equality on the Boltzmann constant. And then you also have, if you have a bipartite graph, chromatic number is 2, Boltzmann constant is bigger than 2 and less than 2, so it has to be exactly 2. And now we reach future directions. So the biggest thing is really that clean result about the asymptotic regularity of gin of any graph is the longest induced path. That's just so pretty. So what we have is this result about the denominators of the vertices, and the denominators correspond to what symbolic power the vertex lies in when you scale it correspondingly. And we have that this, if you take the sum over all the x coordinates when you scale by q, and you subtract by the maximum, we know that the denominator is less than or equal to that maximum. And we have a conjecture that says that it's equal when G doesn't have an induced cycle of size 5 or more, which would be useful in proving the more specific case of the conjecture, but that is still being finagled. And we also are looking at trees, because we literally of this morning have a clean characterization of what the irredundant disconnecting sets of trees look like, and when you add leaves onto it. So hopefully we can prove that this is true for trees as well. And the longest induced path in tree, the length of the longest induced path in trees is just the diameter, which would be very pretty. And yes, now getting to our acknowledgements. Thank you once again to all of the organizers, Eloise, Alexandra, Jack, Luis, and of course our mentors, Pedro, Shah, and Adam. None of this would be possible without you guys. And most importantly, Thank you so much, Charlie, for listening.
All right. So questions for our speakers? Yes, go ahead, design.
You said that the vertices are determined by intersections of at least n facets. Why is it not exactly n facets? Like,
That's a great question. For the reason that facets don't necessarily have to be linearly independent. So for example, if I have x1 plus 2 plus x1 plus x2 plus x3, x2 plus x3 plus x4, and x1 plus x3 plus x4 equals 1, then I necessarily have that x1 plus x2 plus x4 equals 1. So that's the problem, is that you can have n facets being satisfied imply more facets are satisfied.
do you have a way of characterizing which facets are dependent on others?
Great question. Not really. A lot of our proof techniques basically use the fact that if a characterization of a vertex is you pick any direction, you can't move that in that direction in anti-parallel and stay in the symbolic polyhedron because it's convex.
Yeah.
And then so you say, if I have a vertex that satisfies a facet and I pick a direction, then if I pick a direction that doesn't stay on the facet, then I land outside of the symbolic polyhedron when I go the other way, right?
Yeah.
So basically what we're trying to, like what a lot of the proofs do is you play this like slack game where you see what facets give you slack and which ones are restricted. Okay. And that's kind of the issue, is that if you give slack to one facet, you might be breaking another one. And that's like the hardest thing of the whole problem, I'd say.
Yeah.
More questions?
Yes.
You have a result that generalizes something about edge ideals to binomial edge ideals?
To the generic initial ideals of binomial edge ideals.
Okay. How is there like, what was the idea from that? Because like, I don't know, our group had this like miraculous thing where doing a bunch of operations to a binomial edge ideal turned it into an edge ideal, but we like completely changed the structure of the graph we were working in.
Gotcha. Yeah. So this result, they actually proved something much more general, which is they took an edge ideal of a hypergraph, and you can think of any monomial ideal as the edge ideal of a hypergraph. And they said the Walsh-Schmidt constant is exactly the fractional chromatic number over the fractional chromatic number of -1. The difficulty is that it is not an easy problem to compute the fractional chromatic number of the corresponding hypergraph of whatever GIN corresponds to. So this is a more specific extension of their bound for when the hypergraph is just a graph.
Okay.
But yeah, that's a good question. I wonder what kind of intersections our projects have.
More questions? All right, let's thank the speakers again.